So I'm from ReSolved Technologies, is a startup founded in 2020, but the developing of the technology and looking into the subject goes back much longer than that. And what I will tell is a little bit on the edge of the context of this conference, because I will not talk about a hardcore chemical recycling technology, but rather a in-between technology. It's a physical form, but using chemicals. It's a solvent-based technology, which is in the previous presentation was called as a dissolution technology. And I will talk about the recycling opportunities of this technology for engineering plastics. And engineering plastics is maybe not the largest volume, but it is interesting because the recycling of engineering plastics is lagging behind hopelessly. The average recycled content of engineering products, of plastics products made from engineering plastics, is maybe 2%, something like that. So it is really lagging behind. And engineering plastics in general have a rather high, large carbon footprint, anything between 3 kilograms to 7 kilograms of CO2 on a kilogram plastic produced. So it's really, there is a large potential on that. So a few years ago, I have to switch. A few years ago, we have analyzed the plastic value chain and assessed different recycling technologies. We have a report available on that. And our conclusions were that the recycling of plastics is really pretty much on the agenda of brand owners because they care about their circularity performance and carbon footprint. And therefore, there is a growing demand for high-quality recycled plastics to replace virgin resins. And it is important because the large majority of plastics produced or recycled plastics produced today are not replacing virgin resins. Or let's put it that way, they go not back into the original product, but they go into alternative markets, like packaging. Polyethylene is recycled mechanically into pipes rather than closed loop. And engineering plastics is interesting, as I said, from many aspects, but the problem is that they mostly occur in complex waste products, the recycling of which is, any kind of recycling is challenging. And we believe that solvent-based technology, if it made in the right way or carried out in the right way, gives a solution. And mechanical recycling in that sense is, we see it is insufficient to do this. So if we look at a little bit, zoom in a little bit more into the trends, current trends, we have heard a lot today about it, just very shortly. So there is an increasing consumer awareness, which is translated to more stringent legislations, and it increases. The implication is that there is an increasing demand for closed-loop recycling, closed-loop materials actually, and circular materials are now becoming mainstream, at least in the heads of people, and it is very important. So there is also a shift from there towards higher quality recycled materials than the standard is today. And it gives a tremendous opportunity for advanced recycling techniques like chemical recycling, but also for solvent-based. And Europe has the ambition, European Commission at least, to increase the recycling capacity by fourfold in the period between 2015 and 2030. This means that the amount of recycled plastics entering the market will increase, and the impact will be that a lot of current markets will saturate, at least for mechanically recycled plastic. And there is the CO2 price, we have it heard before, that is pretty much on the increase by 1,000% in the last couple of years, and it favors recycling, which is good for us at least. So what are the challenges really in making engineering plastics circular? Well, the plastic or recycling of engineering plastics from anything basically e-waste or car scrap is dominated by mechanical recycling. The problem is only that mechanical recycling has limited capabilities in removing contaminants. And contaminants, the presence of contaminants is a decisive factor in the quality of the recycled plastic made. And this is now the issue because engineering plastics are used for the superior mechanical properties. So if I turn engineering plastic waste by mechanical recycling into recycled plastic, then the quality will suffer. And that's an issue. So closed-loop recycling for engineering plastics from post-consumer waste is often beyond reach, at least for the large part of it. Let's look at an example. For example, ABS and HIPS, which are major engineering plastics. In Europe, in 2018, 1.9 million tons of these materials were used in products, and only 900,000 tons of them were collected as post-consumer waste, and only 70,000 of them were recycled back into new products. So it is really a huge gap, a huge challenge to improve that. So it means that more than 90% of the ABS and HIPS waste is currently downcycled, incinerated, or landfilled. So we think that the solution will be that, let's say, the approach is that e-waste and car scrap are complex waste streams, right? So there is, we have heard it before, there is no easy solution for that, but we believe that these materials, this complex waste stream, require sophisticated approaches. And we also think that especially if materials are to be recycled in a closed loop, the best way to do it is in a consortium. So we need to involve the whole value chain, at least a large part of the value chain, to be successful in it. It is different in open loop recycling, and that is what we have seen in the last decades, that recycling companies are really not relying on the whole value chain because they have their own markets, which were separate from the virgin resin producers. And we also think that combining recycling technologies is the way forward. Because there is no silver bullet, we need smartly combine different types of technologies that are really synergistic to each other. And we have identified that the solvent-based technology is highly synergistic to mechanical recycling. If we combine the two, they are not only much more powerful than other technology or the single technologies, but it's also not double the cost. It is very important, of course. So the solvent-based technology has similar feedstock requirements. So it actually requires the very similar pretreatment process. It produces the same type of product. It doesn't produce an intermediate product like oil or gas or something, but it produces a recycling pellet just like mechanical recycling. But it has it adds in the capabilities to remove contaminants, so we can produce with this combination a much higher quality of recycled plastic. than with the mechanical recycling alone. And we looked at all kinds of recycling technologies. We have basically 5 types, at least what we have identified. It's the mechanical recycling, the solvent-based or dissolution technique, depolymerization, the thermal decomposition, and biological techniques. And if we can roughly divide all of these into 2 categories: the physical recycling, in which the polymer recycling remains intact, and those in which the base polymer is broken down. Now, you see that solvent-based recycling is, in the strict terms of the definition, is not a chemical recycling. It involves a lot of chemicals, but in the end, the base polymer remains intact, so it has a physical kind of recycling, and therefore probably it is highly synergistic to mechanical recycling. And if we put the different types of recycling technologies in the value chain, we see that mechanical recycling is the shortest loop. So if it can produce, and it is preferred, actually, the first choice of recycling, but it is important that it can produce the required quality, and it is where the problem lies, that mechanical recycling in many cases cannot produce the required quality to replace virgin resins, especially not when the feedstock is a complex waste stream. Then we have to look to other techniques, and we think that the solvent-based technique is the right choice, at least for engineering plastics, or many types of engineering plastics. And yet another overview of all these technologies is that not all of them are suitable for all kinds of plastics. Especially depolymerization is only suited for a limited number of plastic types, and pyrolysis also. But mechanical recycling and solvent-based recycling both are suited for a broad range of plastics. And if you look at the plastic types I have listed, at least PVC, ABS, and HIPS, there are no chemical recycling techniques that make really sense. So the only alternative to mechanical recycling, in our view, is the solvent-based technique. And in terms of the quality that can be produced, we have heard already that mechanical recycling has some limitations. Actually, mechanical recycling can produce a broad range of qualities depending on the technology used, but it's still usually relatively limited in quality when compared to virgin resins. On the other hand, chemical recycling produces essentially the same quality as virgin resin, so it is and from quality, in quality terms, is perfect. But the solvent-based technology has a lot of advantages, and in many, even closed-loop recycling applications, it is not the exact virgin quality is not required, but we can be a little bit lower, and the quality that is produced by solvent-based technique is just between the mechanical and chemical recycling, but very close to virgin resin quality. So from all of these aspects, taking into account, we have identified that a hybrid technology, a mechanical pretreatment followed by a solvent-based treatment is the right way to go for engineering plastics, especially from these complex waste streams like e-waste. And that is just what we do. I'm going a little bit forward, faster. So in our hybrid technology, we apply a synergistic combination between between the mechanical pretreatment and our solvent-based technique. Actually, you can see on this graph that the solvent-based purification step is just an additional step that fits perfectly into the mechanical recycling infrastructure. And the beauty of the solvent-based technique is that it offers a lot of opportunities to remove all kinds of contaminants, especially the nasty ones. As we talked about the legacy additives like bromine, flame retardants, but also colorants and softeners and all kinds of things. And we build on proven technology. We acquired a few years ago an existing technology that was extensively tested on a pilot scale, 600 tons per year for quite a number of years. And now we're improving this technique to add additive removal modules to that. And our plan is to build a pilot plant, an integrated pilot plant. It should be ready a year from now. And in 2014, end of 2024, sorry, we are planning a 3,000 ton per year demo plant that we would like to scale up to 10,000 tons a year later. And I would like to tell about this a little bit. We are developing a carbon credit model. We believe, as I said, that if plastics are recycled into in closed loop, then involvement of at least a number of players in the value chain is important. And we would like to involve companies that are further away in the value chain by offering a carbon credit to make cooperation, let's say, a step in easier. And this carbon credit model is based on verifiable CO2 savings. You see the carbon, normally carbon credits are issued from bio-based projects in which CO2 is absorbed from the air, for example, by trees. Our model is based on CO2 savings, but normally this CO2 savings that we produce, that we generate, it has not only a local impact, but it has a impact on the whole value chain. So we not only reduce our own carbon footprint, but the carbon footprint of the whole chain. So from that perspective, we believe that it makes sense to involve other companies by issuing carbon credits from these savings. And another point is that normally, if, for example, I would recycle plastic waste that is already being recycled or potentially today is recyclable, it is very difficult to show what is the net CO2 savings. But we will recycle ultimate waste that is today disposed of on landfill or incinerated. So it means that the net CO2 savings that we can achieve is very easy to show. And also the circularity, because these plastics are now exiting the value chain. If we recycle them back, then we directly improve the circularity performance of these materials. And the CO2 savings are pretty large. For example, for ABS, is the net saving is 2 kilograms of CO2 per kilogram plastic. We think that buying of such carbon credits from parties in the value chain, help them to increase their circularity performance of their products and reduce the carbon footprint. So it's a double carbon credit, we believe, and we call it a CNC credit for carbon and circularity. Thank you very much.